This report covers Lab 4 for Physics 2. The purpose of this lab was to measure the distance dependence of the magnetic field due to a small bar magnet and compare my measurements to the distance dependence predicted by the equations for the on and off axis magnetic fields derived from the Biot-Savart law. I will simulate the magnetic field of a bar magnet via glow script to compare predicted and experimental values, and overall I hope to determine the relationship between the distance and the magnitude of the magnetic field. A quick preview of my main results. I found that as distance increases, the magnitude of the net magnetic field decreases, showing an inverse relationship. I plotted the natural log of the magnetic field versus the natural log of distance in a linearization via the power law relationship, and I saw a straight line which supports the claim that the magnetic field of the bar magnet follows a power law relationship of distance. I determined the value of n in the power law equation to be negative 2.0147. However, my experimental results deviate from the claim that the bar magnet behaves like a dipole, and overall the experimental and computational results do differ. So a quick overview of some physics principles. In terms of the magnetic dipole field, a bar magnet behaves like a magnetic dipole. Its magnetic field decreases with distance, following an inverse cube relationship. We will be utilizing the power law relationship in this lab and assuming that the magnetic field follows it in this experiment to experimentally determine the value of the exponent n. And to do this, we will plot the natural log of the magnetic field versus the natural log of distance to turn the power relationship into a linear relationship, and this will allow us to take the value of the slope as n. A few more physics principles that are important for this lab is that the Biot-Savart law describes how a magnetic field is generated by moving charges or currents and how that field depends on distance and direction. For a bar magnet, this leads to a dipole model where the magnetic field decreases with distance and has different expressions depending on where you measure it along the axis of the magnet or off to the side. Along the axis of the magnetic field points straight along the axis and follows an inverse cube relationship with the distance. Off axis, the magnetic field becomes more complex because it depends on both the distance and angle relative to the magnet, involving multiple vector components. The system is the smartphone magnetometer, which measures the magnetic field components, and the surroundings include the bar magnet producing the field and the Earth's magnetic field. Some assumptions I had to make in this lab was that the bar magnet behaves like an ideal magnetic dipole. I had to assume that the magnetic field follows an inverse cube dependence on distance along the axis, assume the phone is aligned so that the Earth's magnetic field does not significantly affect the x component, and then also assume external magnetic interference is negligible. Overall, these are my experimental results, and the slope of this plot gives n, which represents how the magnetic field depends on distance. However, since the slope is not near -3, the experimental results do deviate from the claim that the bar magnet behaves like a dipole. This is because for a dipole, as distance increases, the field drops off as r is raised to the -3rd power, making the theoretical prediction for n equal to -3. But the intercept of this plot is the natural log of k, which relates to the magnetic moment of the dipole. This is my code, and to find the magnetic moment for my experimental data, I set k with r raised to the n equal to the magnetic field equation for an on-axis dipole, and since I collected data at 5 different r values, I found the magnetic moment for each of those and took the average, which equated to approximately 2.35, as can be seen in my code. And then as we see from the simulation, the magnitude of the magnetic field does decrease with distance from the bar magnet. So my overall results were that as distance increases, the magnitude of the net magnetic field does decrease. Simulated magnetic field off-axis, the magnitude was found to be about 4.78 times 10 to the -5 Tesla, whereas the experimental magnetic field off-axis I found to be about 6.41 times 10 to the -5 Tesla. Some potential sources of error between these are other sources of magnetic fields in the surroundings, slight movements of the phone during measurements. The 1/r cube dipole model prediction only holds if we are far away from the magnet, so maybe we weren't far enough. And we assume that the bar magnet behaves like an ideal dipole in terms of its magnetic properties. However, as we saw in earlier experimental results, the bar magnet did not behave like an ideal dipole in this experiment, so this likely led to the differences between the computational and experimental results. So the discussion. Here are my 2 discussion questions. The first one is, what if the magnet was flipped? Well, if we flip the magnet, it reverses the direction of the field, so b of x would change sign, but the magnitude stays the same, so the results I calculated for n wouldn't change. More specifically, n is not affected because it describes how the magnitude of the magnetic field depends on distance, not its direction. Thus, the sign of b of x will change, but the magnitude at each distance stays the same. If we think back to the graph I plotted with the natural log of the magnetic field versus the natural log of distance, this relationship remains unchanged, so the slope which is n, will also remain unchanged. The other question is, what do you mean by correcting the Earth's magnetic field, which we had to account for in this experiment? Well, the magnetometer measures the sum of all magnetic field presents. In the case of this experiment, its return value is the sum of the bar magnets and Earth's magnetic field contributions. However, the phone alignment specified in this experiment's procedure allowed me to make the x component of Earth's magnetic field approximately zero. Therefore, to isolate the magnet's on-axis field, I can simply calculate b of x. However, for the off-axis measurement, I had to measure Earth's y component separately and subtract it from the experimental value to determine the contribution from the bar magnet alone. Thank you.